This is the 6th video in revision of A-level trigonometry. A reminder then that these videos are aimed at students doing A-level mathematics type courses or similar courses where you're aged roughly 17 to 18. And the intention is not so much to teach the topics as to demonstrate how you might solve typical problems that come up in examinations. And in this particular video we're going to focus on the rule 1 equals cos squared plus sine squared x. Now first of all, just a reminder of where this rule comes from in case you weren't sure. So you take a circle of radius 1, which you see is indicated here. You find an angle x, which is indicated here, and you can work out the vertical height and the horizontal projection. And you'll notice the vertical height is sine x and the horizontal is cos x. Now, it's fairly clear that you've got a right angle triangle in here, so if you apply Pythagoras to this right angle triangle, what you're going to end up with is 1 equals cos squared x plus sine squared x. So in simple terms, that's a sort of a simple proof of where this formula comes from, should you ever forget exactly what the coefficients are. So now what we want to do is focus on using this in problem solving. Some simple questions to start with then. So given cos x equals 0.6, find sine x with 0 less than x less than 90. And the second one is a similar question we'll do in a moment. Now what I'm going to suggest is the simplest solution to this is actually to use this formula. It may not be obvious to you in the first instance, but once we've done it you'll see why. Okay, but I would sketch a figure to make sure I don't make any silly errors. So you'll see what I've done here is I've plotted a figure of sine, which is in blue, and cos, which is in red. And the reason I've done that is I've got my cos and sine curves. I won't make silly mistakes. So first of all, let's look at question 1. It tells me that cos x equals 0.6, and it tells me that x is between 0 and 90. So what I can see is that that corresponds to a point somewhere around here. Okay, I can see that on the figure, and therefore the value of sine x for the same x is going to be somewhere around here. So the advantage of doing this is I can see immediately what sort of solution I expect in case I make a silly mistake. But now let's do the problem properly. So what we know is that cos squared x plus sine squared x equals 1. We're given cos x is 0.6, so we have 0.6 squared plus sine squared x equals 1, or in other words, sine squared x equals 0.64, or in other words, sine x equals plus or minus 0.8. However, looking at our figure, we can see that we only want the positive value, so our answer is going to be sine x equals plus 0.8, not the minus 0.8. Okay, second question then. Second question, we said given sine z equals minus 0.4. So again, let's look at our graph and just have a look where that is, and you can see that's a point somewhere around here. And hence we want to find cos z. Well, if I follow up, you can see the corresponding value of cos z is going to be somewhere around here. But we've actually asked for all the solutions between minus 90 degrees is less than z is less than 90 degrees. But we know that although there are two solutions that give the same value, we obviously only want this one because it has to match the sine z. Anyway, let's get on and use this square rule to solve it. So we've got cos squared z plus sine squared z equals 1. I know what sine z is, so I have cos squared z equals 1 minus 0.4 squared, which is 0.86, and therefore cos z equals, now clearly it's going to be the positive square root of 0.86. We can see that from the figure. And hopefully you'll see that with these solutions I didn't need a calculator, because I haven't been asked to actually find the angle. I've just been asked to find sine x or cos z. So I didn't need a calculator. I could just write down the solutions by inspection. Now a slightly more challenging question. Find the solutions for sine theta tan theta equals 3 cos theta plus 2 in the domain 0 less than or equal to theta less than or equal to 360 degrees. Now it may not be immediately obvious, but these types of questions are usually expecting you to use this sort of formula. 1 equals cos squared x plus sine squared x. Obviously here I'm going to use theta. So what I'm going to do is start by doing that. But before I do that, I'm going to remember, I don't know if you remember this, that tan theta equals sine theta over cos theta. So first of all I'll get rid of the tan. So let's do that first. So I've got sine theta times sine theta over cos theta equals 3 cos theta plus 2. And then I can multiply up both sides by cos theta. So I end up with sine squared theta equals 3 cos squared theta plus 2 cos theta. And now I can see I've got cos and sine, and I want to remove either the cos or the sine. But because I've got two cos terms, a cos squared and a cos, it makes more sense to remove the sine. So I'm going to rewrite the sine squared as 1 minus cos squared theta, and then just rewrite the whole equation. There we go. And now what I can do is put everything on the same side in order to simplify this. So if I bring all the cos squareds across, let's put a line, you're going to end up with 4 cos squared theta plus 2 cos theta minus 1 equals 0. And clearly this is a quadratic in cos theta. So I can use my standard quadratic formula in order to find the roots. So I'm going to write now that cos theta equals, and you're going to get minus 2 plus or minus the square root of 2 squared, which is 4, plus 16, all divided by 8. Or in other words, cos theta equals minus a quarter plus or minus root 20 over 8. Now at this point you're probably going to need to use your calculator, but you'll see that there's two solutions. So my two solutions are going to be 0.309 and minus 0.809. What I've done next is I've plotted my cosine curve, and you'll see I've put that there already and waiting, so that once I've got the values I can actually see where the solutions are. So if I look at 0.309, that's going to give me a solution somewhere around here and somewhere around here. So there's two possible solutions. And if I look at minus 0.809, you can see I've got a solution here and a solution here. So there's going to be 4 possible solutions that I'm looking for here. So first, if I do the 0.309, use your calculator for this, you'll find the basic solution is 72 degrees. So that's that one down there, that's 72. And therefore, I can work out this other one on the far right as being 360 minus 72. So that one must be 288 degrees. If I do the minus 0.809, again, you can use your calculator. You see you get 144 degrees, and that's that one. And then obviously the one that's on the other side of 180 is 216 degrees. So you've got 4 solutions to this particular problem. Question 3 then. Find the solutions for this one. 5 cos squared theta equals 3 times 1 plus sine theta. And again, in the range 0 less than or equal to theta less than or equal to 360 degrees. So again, the first thing to do is remind yourself that we can use this identity where it might be useful. So what I'm going to do is I can see I've got a sine theta on its own, so the logical thing to do is replace this cos squared theta with a sine squared term. So I'm going to get 5 into 1 minus sine squared theta equals 3 into 1 plus sine theta. And now I can combine all common terms, and you'll find you get 5 sine squared theta plus 3 sine theta, and then minus 2 equals 0. And clearly this is a quadratic in sine squared theta. So I can now solve for sine theta using my quadratic formula. So sine theta equals minus 3 plus or minus the square root of 3 squared, which is 9, plus 40, all divided by 10. And that gives me sine theta equals minus 3 plus or minus 7 over 10. In other words, sine theta equals either minus 1 or 0.4. So again, having got the values for sine theta, you'll see that I've sketched down here a sine curve, so we can see where these values lie. Well, the minus 1 is clearly down here, so that's going to correspond to 270 degrees. You can see that one straight away. For 0.4, we've got two values. Or perhaps I should use red. We've got a value here and a value here. So we can quickly work out what they are. The first solution is 23.6 degrees. That's that one there. And obviously this solution here is going to be 180 minus 23.6, so it's 156.4 degrees. Question 4. Solve this one. 3 sine squared theta plus 7 sine theta equals cos squared theta minus 4. Now, as before, what we're doing is we're saying, look, this has got a sine theta term on its own, so I can't eliminate that. So the logical thing is to eliminate this cos squared in terms of sine squared. So I'm going to rewrite this as 3 sine squared theta plus 7 sine theta equals 1 minus sine squared theta minus 4. And now what I can do is I can combine all the terms together. So I get 4 sine squared theta plus 7 sine theta plus 3 equals 0, which is a quadratic in terms of sine squared theta. So now using my quadratic formula to find the roots, I can write sine theta equals minus 7 plus or minus the square root of 49 minus 48, all divided by 8. And what that's going to give me is minus 7 plus or minus 1 over 8, or in other words, you're going to get minus 1 or minus 0.75. So again, you'll see I've plotted my sine curve, so once I've got these two solutions, I can see where they appear on the sine curve. So the minus 1, there it is, down there, so that's going to give you 270 degrees, and the minus 0.75 is going to give you a solution here and a solution here. So I can work out what they are. They're going to, one of them is 228.6 degrees. You can use your calculator for that, and one of them is 311.4 degrees. Now, if you stick it in your calculator, it's quite possible that this will give you a solution. I'm going to write it here, minus 48.6 degrees. And clearly, that isn't the solution that you're looking for, because you're told, I want a solution in this range here. But remember, once you've got the minus 48.6, you can just add 360 in order to get to the corresponding point, which would be this one. So minus 48.6 plus 360 would give you that point, and once you've got that point, you can find the other one. Final question then. Solve this one. 4 sine squared z plus 9 cos z minus 6 equals 0. And again, you'll see because I have a cos z on its own, I can't easily eliminate that, so I'm going to eliminate the sine from this term here. So I'm going to write 4 into 1 minus cos squared z plus 9 cos z minus 6 equals 0. And then join all the common terms together, so I get 4 cos squared z minus 9 cos z plus 2 equals 0. And that's clearly a quadratic in terms of cos z, so I can use my quadratic formula to solve for cos z. So cos z equals, and I'm going to get 9 plus or minus the square root of 81 minus 32, all divided by 8. Now this may seem to be a messy one, but it's not as messy as it looks, because you'll find this gives you 9 plus or minus 7 over 8, and that's going to give you either 2 or minus a quarter. Now the thing here is you clearly cannot have cos z equals 2, because 2 is bigger than the limit to cos z, which is 1. So I don't need to consider that solution any further. I can now just look at the solution minus a quarter. So where does minus a quarter appear on my cosine curve? You can see it appears roughly here and roughly here. So these are the two solutions I'm looking for. So if I solve that, if I solve for cos z equals minus 0.25, you'll see you get z equals, should I have said minus a quarter? Sorry, that should be plus a quarter. I do apologise. That's plus a quarter. That was a rather careless mistake. There it is. Let's put the solution up there. That makes life a bit easier. So we've got a solution there. So z equals 75.5 and 284.5. Finally then, there are many other scenarios where you might find this formula useful, and one obvious one is the equation of a circle, where you have things like x squared plus y squared equals a squared. And in such case, you can substitute using this formula. So you can do things like write x equals a cos theta, y equals a sine theta, and that gives you a different way of expressing the equation for a circle. If a formula contains both cos squared and sine squared terms, which will happen quite often, then you can easily remove one and replace it in terms of the other. So the key thing to recognise is if you've got both terms, if you use this formula, you can get rid of one of them, and that was going to appear many, many times in real problem solving.